I got everything done. I got. Was gonna have.
Test. Just making sure the audio's fine in here. Hang on. I think, yeah, this is good.
Okay, good morning. 5C and 5D. Okay, thanks,
Good morning.
Rocco.
Should probably note, I forgot the microphone today, so you're not gonna get classroom audio. I've put a note on the board though, telling people to join on their phone.
Diana, right?
What?
Who's talking?
Arthur.
Hi, Arthur. I don't know you, so I don't recognize your voice. Okay. Are you all set up?
Uh, again, we don't. I forgot the microphone today, so you're not gonna get audio from the classroom. But I have I can't really flip around the camera, but I've just told people join on the phone.
All right. So, yeah, you join on the phone. If you don't have a microphone, please join on the phone. Okay, so let us get started with your questions and then we proceed. So it is the review, and I will look at them. Zoe asked for problem number 4B, of course, and Rocco asked for 5C and 5D. Did I assign 5? I don't think I assigned problem number 5. I assigned 1 to 4, unless I did a mistake. Okay, all right. So I'll keep one. Okay, I'll keep them. I will use them as okay, 4 and 5. Okay, 5. Okay, 5A and D. 5C and 5D. Okay, no problem. Okay, so first I start with Zoe's question because it's I have to go through it. So Zoe's question is she wants problem number 4B. Very good. So I'm gonna use your questions to model the lecture around them. So every problem you ask will be answered throughout the lecture. Any other question beside those? Okay, so Zoe's question will be answered very soon as well as Rocco's question. So let me ask you first, just to recall something simple. So, question. Okay, I want you to use the geometric interpretation of the integral to answer the following. I'm going to give you a function f. That's my function. And this is half a circle. So this is a 2 in here. And this is, I'm just going to make up number. This is going to be like a 3 in here. And this is the point 3, 4. And this is the graph of a function f of x. So very quickly, I want the following answers. What is the integral from 0 to 2 of f of x dx? And right now, I'm only asking you to use the geometric interpretation of the integral. So what's the integral from 0 to 2 of f of x dx? So this is f. And this is my function. What's the integral?
wouldn't it be the infinite Riemann sums of that area under the curve?
Yeah, it's the limit of the Riemann sum, but I want its value using the geometric interpretation of the Riemann sum. This time I wanted to use the geometric interpretation. And this, to be very clear, that's half a circle. So you know exactly what I am talking about. It's pi over 2. Ooh, how are you getting pi over 2? Jonah, can you mute yourself and explain to us? Okay, anybody else? So what's the geometric interpretation of the definite integral? It is the limit of the Riemann sum, 100% correct. But what does the Riemann sum represent in this scenario? Remember, when we start evaluating f of xi times delta x between 0 and 2, what are we supposed to get?
The net area.
The area, not exactly, you're half correct. How is the form? 2 minus pi over 2? Why 2 minus pi over 2? So the integral is from 0, these are the limit, all the way to 2. So it's from 0 to 2, so these are my limit. Yeah, that's okay. That's from 0 to 2. These are my limits. So it means I'm looking at this piece of the graph. Exactly. Yeah, that's all right. So what's Mr. Exactly. So what's going to be this? It's the function here. Let us note f of x is negative on the interval 0, 2. Absolutely negative. So this is the integral is not the area, is minus because the function is negative. So it's minus the area under the graph of f on the interval 0, 2. It's not the area, it's minus the area because the function is negative. Exactly. So that's equal to minus. Now what's the area here? Okay, because it is the Riemann sum, but when we start adding them up geometrically, it's going to give me this area. So what is the area? So that's a half circle. So the area here is half pi times the radius square. The radius, if from here to here is 1, the radius is 1. So the area is 1/2 pi, or pi over 2. So the value of this integral is minus pi over 2. Okay, we're just reviewing the geometric interpretation of the definite integral. So it's minus because the function is absolutely taking negative value. So when we are adding those sums, we're getting negative value. And in this case, because it's a half a circle, actually I can find the exact value, which is the area. Okay, and now example number 2, the second question. What's the integral? And now that's what Gustavo didn't pay attention to, the integral from 0 to 3 of f of x dx. Now 0 to 3, this is 0 and this is 3. So this is telling me that I'm interested in the integral from here to here. So this is giving me the limit. And now back to you. What's the integral from 0 to 3 of f of x dx? Now I want all of you to be part of it and answer.
Wouldn't it be the area of the triangle, which is 2 minus pi over 2?
Right. The area of here, so between 2 and 3, the function is positive. So the Riemann sum, the sum of the Riemann sum will give me the exact area under this graph. And the area here is, area of a triangle is a half. The base from 2 to 3, it's a 1, times the height, which is a 4, the area is equal to 2. So the integral is, when the function is negative, it's minus the area, plus when the function is positive is plus the area. So that's really the definite integral. So the definite integral, if the function is positive, is the area, otherwise it's what we call the net area. Okay, so that's a quick recall for the geometric interpretation. Now we are going to go back to what your classmate said, that so let us recall now. Okay, let us recall that what was our definition for the integral. So the definition is the following. We take the interval AB, we split it into pieces, and we take the Riemann sum, I equal 1 to n. We evaluate the sum for larger and larger value of n. And when n becomes very large, those sum become close to a fixed number, is what we call it the definite integral. Okay, so that was our definition of definite integral. And geometrically, as I started the lecture, is the area, as long as the function is positive, is the net area if the function start taking positive and negative value. All right, so that's really the definition. But now what's the issue? The issue is evaluating those sums, as you realize, is very hard. So we cannot just evaluate them. I mean, I gave you for your homework, a computer algebra system to be able to evaluate it. So there is a theorem, as we saw in Calculus 1, which make evaluating those sums easy for some function. So let us recall the fundamental theorem of calculus. So the fundamental theorem of calculus is the most powerful tool in calculus to help us evaluate this integral. It's not the definition, it's a tremendous tool though. The fundamental theorem of calculus. Okay. Tells us the following, that if I know an antiderivative of the function f is an antiderivative of the function f, means if I know an antiderivative of the function, then we have a way to evaluate this definite integral. It means this messed up sum as follows. So the indefinite integral is the value of the antiderivative at the upper limit minus its value at the lower limit. So the fundamental theorem of calculus gives us a tremendous tool to evaluate this sum. And as you recall in calculus 1, f of b minus f of a, we use the following notation to write it. We write this as f of x, and then we put a bar to the right, not to the left. We put the bar to the right, a, the lower limit, and b. Okay, so the notation in this course and every math course is actually crucial. So the fundamental theorem is, as I said, the tool to evaluate those definite integrals. So we're going to practice the fundamental theorem for several problems. Okay. Please, when I move the paper, if you are not ready, you let me know, because you have to help me to see what you guys are doing. So example number 1. A very easy example. Okay. The question is, use the fundamental theorem of calculus to evaluate. Yesterday in class, we did the following example, if you guys remember. We evaluate basically the Riemann sums for this function. That's what we did yesterday in class. And if you guys recall, we get something like 8.66. So we got this answer by evaluating Riemann sum over and over. So today we are going to use the fundamental theorem to be able basically to get the answer. So the fundamental theorem tells me to evaluate this, we need an antiderivative of x squared. So we know the antiderivative. So the first way, I'm going to do it the slow way. So here f of x is x squared. We need an antiderivative. Is f of x equal 1/3 x cubed? So the fundamental theorem would tells me that this is equal to actually plus c. That's the exact format. It's the antiderivative. You evaluate it between the lower limit and the upper limit. That's the notation we use. And this bar to the right, as I said. So it's equal to the value of the antiderivative at the upper limit minus at the lower limit. So at the upper limit, it means I plug in 3 for x, add a c, minus at the lower limit, plus c. And now I evaluate. This is equal to 3 to the power 3 is 27. 27 divided by 3, which is going to give me a 9, plus c, minus 1/3, minus c. Now remember that the definite integral is a number. Geometrically, it represents the area under the graph of x squared between 1 and 3. So the answer should not have a constant in it because it's actually a number. So we should not have plus c because it's a unique number. So all the time, the c and the minus c have to cancel out. So because of this reason, whenever we find a definite integral, we don't write plus c in the antiderivative because it actually confuses us more than anything else. So finally, I will get 9 minus 1/3, it means 27 minus 1, 23 over 3. So that's the exact value, which is very much what we got yesterday. This is as recall. Yesterday, when we evaluated the Riemann sum, we actually got 8.666, which is exactly 23 over 6. But the fundamental theorem is absolutely giving us this tremendous tool to avoid the Riemann sum. The problem with it is that we need an antiderivative. So if we cannot find an antiderivative, actually we cannot use the fundamental theorem. That's why we will spend a lot of time focusing on finding the antiderivative. Right. Example number 2, which is going to be one of the questions that your classmate asked. So I'm going to do it. Question, please. Okay. So I will do problem number 5. And I will do C because your classmate asked for number C. So we're going to do that. And the question is, I wanted you to evaluate. By mistake, I assigned number 4. I didn't have that in mind. Integral from 1 to 4 of the following. 4 plus 6y divided by the square root of y dy. Okay? So what the fundamental theorem of calculus tells me is that what you really care about is an antiderivative. So once I know how to find the antiderivative, I am okay. I can use the fundamental theorem very easily. So for the time being, let us say, ignore a little bit the limit and focus on the antiderivative. So that's really what I need. So we need antiderivative or indefinite integral. So we need the antiderivative. That's the heart of it. That's what we need. Okay, so if you want an antiderivative of this, let us remember how would you do it? Help me out quickly. How would you find the antiderivative of this function? I'm listening.
Could you split it up? So 4 over root y plus 6y over root y?
Yeah, we can do that. Absolutely correct. Uh, or, 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 both will be correct. 4 plus 6y, what you said verbatim is correct, but I can multiply it by what? Remember, integral calculus doesn't like the square root. So this is immediately y to the half, immediately, because we can't work with it. So, or you can do that and you multiply it by y to the minus a half. Okay, so I'm just focusing on antiderivative because that's really what the whole thing is about. So this would give me the following. Integral, so far I'm getting ready to find antiderivative. 4 times y to the minus a half plus 6 y to the half, the whole thing dy. Okay, so now we evaluate. So that's the integral from 1. No, actually, I don't need that. Now we are ready to find the antiderivative. So I'm going to put the big parentheses here. And from 1 to 4, and let us find the antiderivative. 4 is a constant. Antiderivative of y to the minus a half is 1 over minus a half plus 1. Minus a half plus 1 is a half. So this is really like multiplying by 2 to the power a half plus 6 is a constant. Y to the half is 1 over a half plus 1. Y to the half plus 1. Okay. And finally, this is equal to, not finally, I have to simplify before I proceed in the evaluation. This will give me 8, if you want, y to the half or the square root of y, plus a half plus 1 is 3 halves. So it's 6 times 2. So it's going to give me 12 divided by 3, which is a 4 y to the power 3 half. Okay, if I do any mistake, you please let me know. Now we do the evaluation. So it's everything at the upper limit minus everything at the lower limit. So that's f of b minus f of a. Okay, now at the upper limit, it means 8 times y is 4. Basically, it's the square root of 4 plus 4 times y to the power 3 half. It means 4 to the power 3 half. But let us remember, y to the 3 half means the square root of y to the power 3. Okay, so I'm going to substitute this. So that's going to give me square root of 4 to the power 3. Evaluation at the upper minus evaluation at the lower. The lower is 1. So it's going to give me 8 plus 4. So finally, I will have 16 plus square root of 4 is 2 to the power 3 is 8. 8 times 4, 32 minus 12. And finally, I will get the following. 16 minus 12 is a 4. 4 plus 32, which give me 36. Okay? Any questions about this problem? So fundamental theorem of calculus, I mean, imagine using Riemann sum to evaluate this. This will be nothing but a nightmare in the making. Any questions? Okay. Example number 2 is going to be basically the problem that I assigned. Number D, please do it again. And you ask me tomorrow. Remember the arc sign. Okay, actually, I'll do it just to finish with it. 5, number D, we have the integral from a half to square root of 3 over 2 of 6 over the square root of 1 minus t squared dt. Sorry, if you don't see very well, you let me know. One minus t squared dt. Again, the whole thing is to find the antiderivative of this function. Now 6 is a constant. I can always take it out. And then I'll be left with the integral from a half to the square root of 3 over 2, 1 over square root of 1 minus t squared dt. And now quickly, what's the antiderivative of this function? What's the function whose derivative is 1 over the square root of 1 minus t squared? Back to you. That's the arc. Exactly. So that's arc sine of t evaluated between a half and the square root of 3 over 2. So finally, that's 6 times at the upper minus the lower. So that will give me arc sine the square root of 3 over 2 minus arc sine a half. So it's 6 times. Now, what is arc sine square root of 3 over 2? What is the angle whose sine is square root of 3 over 2? Remember those? I expect you to know those. What's the angle whose sine is square root of 3 over 2?
Is it pi over 6?
That's no.
Uh-oh.
That's the pi over 3. And what's the angle whose sine is a half? That's the pi over 6. Okay. And then finally, I will multiply this by 2. I will have 2 pi minus pi. So I'm going to end up with pi, right? I'll end up with pi. Okay. Very good. Right. Now I'm going to do problem number 4b because I planned to do that problem, whether you've asked or not. So let me go to problem number 4 on your homework. Okay. Which is again an application of the fundamental theorem of calculus. So number 4. All right. The idea is I gave you the following. In number 4, I told you I took the interval 0 pi. I took the interval 0 pi and we split it into a bunch of pieces. N pieces. I did not give you a specific value. And the question is, so we divide 0 pi into n pieces, and we let our n to be the following. Sigma sine of xi times the delta x, I equal 1 to n. So in my mind right now, when I see this, I start seeing the following. This is a Riemann sum. And this is a Riemann sum for which function? That's the Riemann sum for the function sine x. So it's basically I'm taking the function sine x. That's the sine x function. And what I'm taking is the Riemann sum for that function. Are you with me so far? So question is the following. Question number B. Question is, express if I take the limit as n tends to infinity of this sum. My question is, do you see a definite integral in this limit? Means when you see this limit, do you see a definite integral? Which definite integral? What are the limit and what is the function? The idea is when you see that, I want you to start seeing a Riemann sum. And we take the limit. I want you to start seeing a definite integral. So what's the definite integral here? That's going to be the integral. The function is the sine x dx. That's how we read it. And the limit, what's the upper and the lower, are you look at which interval you split into pieces to get the sum. So that's going to be the integral from 0 to pi of sine x dx. So this is the Riemann sum. We're taking the limit. This is, by definition of definite integral, that's the integral from 0 to pi of sine x dx. And now in the problem, I did ask you to find the limit, to find the Riemann sum for subdivision. And then I told you to use a website to do it for 100 subdivision and the website to do it for 150 subdivision. And the answer should have been, if you do it for 4 subdivision, you should have gotten 1896. For 100, you should have gotten, just by clicking the number, 1.998. And this is 1.999. So if I start taking those things, that's the answer I get. So the natural answer then for this should be, according to the Riemann sum, should be almost a 2. So the Riemann sum suggests a 2. So now I ask you also, once you recognize this as an integral, use the fundamental theorem and evaluate the sum. We should get almost 2 because that's what the Riemann sum are giving me. But now the fundamental theorem will give me an easy tool to find it. So by the fundamental theorem of calculus, I should get antiderivative of sine is the minus cosine evaluated between 0 and pi. Means equal to, at the upper minus the lower, minus cosine pi minus cosine of 0. So that's, I should get that. Otherwise, something is off. Now, cosine pi is minus 1 times minus, I get that. Minus minus plus. The cosine of 0 equal to 1, and this would give me a 2. So you can see how easy to use the theorem. That's why it's called the fundamental theorem of calculus, and how hard it is to find the sum of those. Okay, so that's really the power of this theorem. But that's the important idea. The important idea that when you see this sum, I want you to start seeing a definite integral. Any other questions? Right. One more problem before we move to definite integral and substitution, which will wrap up the review for calculus 2. So one more question is the following. Find the area. So I will call this example. I usually lose track of the example. Find the area of the region bounded by the area of the region bounded by the graph of the function y equal 1 over 1 plus x squared, the x-axis, and the lines x equal 0 and x equal to 1. Okay, so find the area of the region. Tomorrow, we're going to start working more and more with area. And the first thing we will learn is that whenever you are asked to find the area of anything, you sketch. So we're going to sketch. 1 over 1 plus x squared, this is a decreasing function. If x is 0, it's a 1. And like this. So that's the graph of 1 over 1 plus x squared. And the region is bounded by the graph the x-axis, that's what we mean by this, x equal to 0, which is the y-axis, x equal to 1, which is this right there. So I'm interested in this region. And the question is find the area. Now, what is the area? The area is the integral from 0 to 1 of 1 over of the function itself. So now we have the fundamental theorem at our disposal. So to find the area, I don't have to take Riemann sum. I can just use the fundamental theorem. So the area is the integral, because that's what I'm interested in, from here to here, 1 over 1 plus x squared dx. So now to find this area, the fundamental theorem really helped me tremendously. So 1 over 1 plus x squared, what's the antiderivative of this function quickly? Quickly. That's the arctangent. Evaluated between 0 and 1. So finally, I will get arctangent of 1 minus arctangent of 0. Now, what's the arctangent of 1? What is the angle? When you take its tangent, you get 1. Remember, arctangent is the angle whose tangent is 1. Okay, scratch your head. What is the angle whose tangent is 1? Try to answer the questions. Even if you don't say it, remember it in your mind. What's the angle whose tangent of 1? It means tangent of what is 1? 45 degrees, correct. But remember, for calculus, we don't work with degree ever. We only work with gradient. So that's the pi over 4. Because tangent pi over 4 is 1. Minus the tangent of 0. Which angle, tangent of what, is equal to 0? Tangent 0 equal to 0. So this is equal to pi over 4. So the area of this region, we could have taken the Riemann sum, but it's a nightmare to do it. Now we can find the area almost without any sweat, because the area, which is the limit of those Riemann sum, is this integral. The fundamental theorem of calculus is allowing me to compute those with a tremendous ease, as long as I know how to find the antiderivative. Okay. Questions, please ask questions if you have any. Very good. Now, the last thing we're going to review is definite integral and substitution. So I repeat that to use the fundamental, I know to find antiderivative. And to find the antiderivative so far, either we have basic integral or we need to use substitution. So now we will use the fundamental theorem of calculus for definite integral. So definite integral and substitution. And substitution. So we elaborate by an example, and I will take a relatively easy example. So evaluate the following. Integral from 0 to 4 of the square root of 1 plus, I don't know, 5x dx. Okay. So we need to evaluate this integral. And what we have to find is antiderivative of this function. So we will do this problem as we did in calculus 1 in 2 ways. So the first approach is the following. What I need is an antiderivative. So we're going to find an antiderivative of this function. That's really what I need. And then I use the fundamental theorem. And then use the fundamental theorem. So I need the antiderivative of that. So I forget for a little bit about 0 and 4, and I focus totally on the antiderivative. And the reason we use this notation for indefinite integral is because of the fundamental theorem. That's why this notation is used for indefinite integral. All right, how can I find the antiderivative of this function? Do I need a substitution, yes or not? Back to you. Yes, as long as I have an inside function, there is a substitution in the process. I don't have square root of x. I don't have that. I have a function inside. And its derivative is a constant. And we know constant do not give us any problem. So we're going to put the u to be my inside function. And then we're going to find its derivative. Derivative of 1 plus 5x is 5 times dx. And now, as we said, we keep an eye on here, but now I have to go back and start the substitution process. Everything in terms of the new variable. So this would give me the square root of u for this piece here times dx. Now I have to go back and pick up the x from the du, but I don't have quite the dx. I have 5 dx, so we're going to divide by 5 both sides. And this will give me 1 over 5 du is my dx. So my dx now is 1 over 5 du. And now I evaluate this integral as an integral in u. 1 over 5, I can take it out. The integral, it's a constant. The square root of u, I have to put it u to the power a half du. So I am absolutely finding the antiderivative now, totally. So this will end up giving me 1 over 5. Antiderivative of that is 1 over a half plus 1 u to the half plus 1. And because at the end, I am after a definite, I don't worry about constant at all. So this will give me 1 over 5 times 1 half plus 1, 3 half, 2/3 times u to the power 3 half. I have an integral in x. I have to go back to my variable, 2 over 15, 1 plus 5x to the power 3 half. Okay, so far, I've totally found the antiderivative. That's everything I did. And now use the fundamental theorem of calculus. I go back to my definite integral. Integral from 0 to 4 of the square root of 1 plus 5x dx is my antiderivative, whatever it is, evaluated between 0 and 4, which is equal to 2 over 15 times 1 plus 5x, evaluate to the power 3 half, evaluated between 0 and 4. This is equal to the following. I evaluate at the upper limit, so it's 2 over 15 times. If x is 4, 1 plus 20, that's 21, to the power 3 half, minus 2 over 15. If I plug in 0, I will have 1. So this will be equal to, you can keep it like this. You can factor out the 2 over 15, leaving me with 21 to the power 3 half minus 1. Okay, so that's the first approach to the definite integral with substitution. So the idea is in method number 1, you forget a little bit about the limit. You evaluate the antiderivative as a function of x, and that's important. Once you find as a function of x, you use the fundamental theorem of calculus. Now, a second approach. Do you guys remember what the second approach was? If we need to do substitution, you remember the second approach.
You could like plug the two values into the substitution of u
Yes,
and then just put those as the upper and lower limit.
and never go back to x.
Yeah, exactly.
Never go back. So let us do the second method. So we have here the integral from 0 to 4 of the square root of 1 plus 5x dx. The bottom line is we have to find antiderivative. I mean, that's really what it is. So to find the antiderivative, there is one approach for this problem, which is the substitution. So we're going to do the substitution, u equal 1 plus 5x. And then the du, so it's the same thing as before, 5 dx. Everything verbatim. The change is going to be at this stage. We're going to change the limit, and never go back to x. So I will explain this. And do not go back to x. Okay, what do I mean by that? I mean by this, when you introduce your u, you ask yourself, the lower limit, 0 and 4 belong to x. Now we're going to change them so they belong to u. What do I mean by that? You say, okay, if x is 0, that's the lower limit, then I substitute 0 in the expression of u. U is 1. If x is 4, my new limit would be 21. And this is where the change is. This is going to be equal to everything. Now I'm going to put it in terms of u. The 0 now became the 1. The 4 now is 21. Everything in terms of u. Square root of 1 plus 5x is exactly the square root of u. And the dx is 1 over 5 du. Okay. Once I do this, if I change the limit here, I'm creating a whole new integral in u. I don't go back to x anymore. So at this stage, because I changed the limit, I forget totally about x, and I work with this new integral in u. So, which is sometimes easier. Now I evaluate this. 1 over 5 is a constant. I pull it out, and then I will have the integral from 1 to 21 of u to the half du. And I evaluate that as an integral in u. No more x's for me. I'm done with x. U to the half is 2/3. U to the power 3/2. And then this is have its new limit of 1 to 21. So finally, this would give me 1 over 5 times the value at the upper minus the value at the lower. At the upper, I will have 2/3, 21 to the 3/2. At the lower, I will have 2/3 times 1 to the 3/2. Now, of course, we will never leave 1 to the 3/2 because we know better than that. So finally, I will have 1 over 5 times 2/3, 21 to the 3/2 minus 2/3. Now I can pull the 2/3 out because it's a common factor. And then I will have 2 over 15, 21 to the 3/2 minus 1. End of the problem. So substitution, definite integral, is verbatim like regular substitution, but you can either do the substitution without limit, go back to x, and use the limit on x on your antiderivative. Or you can change the limit at the beginning, create a new limit which belongs to you. At this stage, you don't have to go back to x, and then you proceed in the problem. So it's the same thing, but with some changes in terms of the limit. Okay. Any questions before we finish? Now, with this, I've finished the review for Calculus 2, from Calculus 1 to Calculus 2. Tomorrow, we start the new material. Another thing about tomorrow, as you guys know, tomorrow is your first quiz, and it will be given online. I will put the quiz on Brightspace, and you guys will take the quiz, print it if you can. Hopefully, you take it and then you will upload it back into Brightspace. Now, it's very important that you guys today practice how you upload it as a PDF file, because otherwise I will have hard time reading your your quiz. So please practice today how you can transform whatever you have in mind into a PDF file. So I will put the quiz on Brightspace around 11:30. I'll open it. We will only have from 11 to 12. No, I will give you a little bit extra time because you guys will have to upload it. Don't worry about the time. So I will give you enough time. Not all the afternoon, but I'll give you enough time for you to do that. The quiz will be opened at 11:30 because we will have lectures as usual before. And two things. First, I know that I cannot see you and you guys can cheat. I have to call to your honesty not to do that. Please do not cheat because your exam is going to be in the testing center. So try not to cheat so you can do mistakes and I can help you out, or you will never know what you're doing right or wrong. Second, for the students who don't know me very well, I usually do not allow calculators. So your calculator will not be allowed on the test. So for tomorrow, try not to use it so you can practice how you will do the test. So you will not be surprised on the test day that you don't have anything. So again, the only thing I care about that you guys figure out how to put your document as a PDF document, and you can either scan it and upload it into Brightspace for me tomorrow. Any other question before I let you go? And the quiz will cover everything we've done so far. I mean, review 1 and review 2.
So I upload my work on Brightspace and then you grade that work. So I could put like, oh, this worked for question 1, 2, 3, 3.
Exactly. Try to do them in order so I can to make it easy for me to grade them. And then I'll grade them on Brightspace and I will give you like regular. I will give you the correction and everything on Brightspace.
Sounds good. Thank you.
Okay. Any other questions? Okay. Bye guys and have a good rest of the day. See you tomorrow. Yes, you are taking the quiz during class time. Yes, Zoe. Anything else?
Bye, Professor Elias. Have a good day.
Bye-bye.